And we're recording. Okay. So now that we kind of have the situation laid out, we can answer things a little bit more quickly. So in that same scenario, part B, how fast is the surface area changing? So we want to give ourselves a target. So on this one, we're looking for dAdr, the rate of change of area with respect to the radius. All right. So we need to find then an equation that relates the surface area to the radius. So before we can find the derivative, we need the position equation. Well, we already know what that is, right? So the surface area of a sphere is 4 pi r squared. So that's another equation that you need to memorize. Let me see, I'll do the peach, right? So we got the volume up here, and then we got the surface area. But remember, it's just the derivative, right? The area is just the derivative of the volume. And now that I have that equation, I'll take the derivative of both sides with respect to r. So ddr, that's the verb, colon, it says that's what I'm doing. And the derivative of a is dAdr. And on the right side, power rule again, right? Multiply, you get 8 pi r to the first. So there's your rate equation. This down here is your quote unquote position equation. And this is your quote unquote velocity equation. One of them just tells you what the area is at a moment. And now the derivative tells you how fast it's changing, right? Oops, I forgot a card. Put that back later. Okay, and now we can plug in. So again, you always have to indicate what you're doing when you go from a variable to plug in. So in Leibniz notation, again, the easiest way is just to say dAdr when r equals, and it's the same moment in time, when r equals 3. All right, and then we plug in and we get 8 pi times 3, which of course ends up being 24 pi. And then we need units, right? This is supposed to be working down like this. There we go. So if you don't know what the units are, I don't want to say stoichiometry, but dimensional analysis, Leibniz notation will tell you units of area divided by units of radius. So that would be square feet per foot, right? Square feet per foot. If you divided out those units, you would get units of feet, right? Which doesn't really make sense in this context. So we don't want to do that. So here's the sentence, right? Same thing. When r equals 3 feet, comma. You could even say when d, the diameter, equals 6 if you want, if you've called it d, which we have. When r equals 3 feet, comma, the surface area, and again, these are scalar quantities, is decreasing. Everything's getting smaller. Is decreasing by 24 pi. And then what units would we put at the end? Can I just throw feet squared slash feet? Feet squared per. Very good. Very good. Units of surface area, which is going to be square feet, and then per foot. So if you want to get in the habit of changing that last per to some other word, like each foot or every foot, or later on every second or every mile or every gallon, that might help you when you're writing your sentence, because everything else that comes before that should be in unit form. Okay. All right. And then the last one, how fast is the diameter changing? So in this one, we're looking for the derivative of d, which maybe was a poor choice of letter right over here when I called the diameter little d. Maybe calling it big D would be better, but we're looking for this right here. There's our target, the derivative of diameter d with respect to r. Well, before we can find the derivative, the rate equation, I need to find an equation that relates the diameter to the radius. And we know what that is, right? D equals 2r. So once again, this is your quote unquote position equation. It doesn't tell you how anything's changing, but if you know the radius, you can find the diameter. If you know the diameter, you can find the radius at that moment. We want the derivative. So the derivative with respect to r, colon. And again, this is the verb. At this point, we don't put ddr. That's just telling the user what you're doing. The derivative of this side is this, right? Or d prime. And this equals 2, right? It's a constant. So there's nowhere to plug in. Now, even though your equation is a constant, you still want to make sure you're answering the question. So underneath there now we'll say the derivative of the diameter with respect to the radius evaluated when the radius is 3. Same moment in time. And of course, now we'll profess it to be 2. 2. And then units. Units of diameter divided by units of radius. So that should be feet divided by feet. So in your numeric answer, you can have the units all stacked up there. That's fine. Your numeric answer, you do want to put units on your final answer. Feet per foot, right? And you don't want to divide those out because then you get no units at all. Feet per foot, very good. So here's the sentence, right? Again, when r equals 3 feet. That's answering it like an engineer. Instead of saying when the radius of the sphere is 3 feet. That's too many words. When r equals 3 feet, don't forget the units, comma, the diameter is decreasing at a rate of, or you could just say by 2 feet, 2 feet per foot. So yeah, this is like a multi-page kid story if you want to write it at the end. The story of the shrinking sphere, right? And every page is a different quantity. What's happening to the volume? What's happening to the surface area? What's happening to the diameter? Oh no. And then someone gets claustrophobic, right? Because they feel the sphere is enclosing in on them, right? Did you ever read that book, The Monster at the End of the Book, starring Grover from Sesame Street? You ever read that? It's a great book. They've remade it. And the whole time it says there's a monster at the end of the book. And Grover, the cute little monster, is terrified. And he's begging you as you're reading not to turn the page. And you turn it anyway because you're reading, right? And then he's like building a brick wall to try and prevent you from turning it. And then you turn it and the brick wall's destroyed. And he's like, oh no, we're getting closer. And then at the end, you turn to the last page and guess who the monster at the end of the book is? No, it's Margaret Thatcher. Whoa, you've read it. Yeah. It's Grover. It's Grover himself. And he's like, oh, I'm the monster. I'm the monster. Not all monsters are bad, right? I guess Elmo was also considered a monster, right? You know who the real monster was, though, is the original puppeteer of Elmo. Yeah, look that up. I don't want to even get into that, but child molester type stuff. Right? Barney, yeah. All right, so, yeah, oh, I forgot. All right, so here we go. It's in a box. We should memorize it. The volume of the sphere, 4/3 pi r cubed. 4/3 pi r cubed. Memorize it. Surface area of a sphere, S or A. I called it A. You can call it S for surface area. 4 pi r squared. It's the derivative with respect to r. Memorize it. Know it. And then the shape of the sphere, round, roundish, spherical, right? Spherical, right? Define a word with a dog. Got it? All right. Moving on now. The next thing that we're going to get into is one of the most important applications of the derivative. It's when we're talking about the rate of change, not of the size of geometric shapes, but the rate of change of position, the rate of change of velocity, and even the rate of change of acceleration. We can talk about that. This is the Galilean or the Newtonian perspective. All of these bullet points here are summarizing what we're going to be talking about. So rather than go through these and then do the problems, we'll just do the problems and I'll address them as they arise. And then you can refer back to this. It's kind of like a formula sheet. But in the end, you're going to have to memorize, okay? Now, we're going to learn it all in context. And if you've had physics or, you understand how things move, it should be somewhat intuitive to you, okay? All right, so here we go. These make classic free response questions. A particle moves on a horizontal line. That's classic, all right? So you can right there imagine that you've got like an x-axis, right? And here's 0. This is just a random x-axis. And then you got this little particle dude, right? I mean, what does he look like? He looks maybe like a dot. And the x-axis is just there to kind of keep track of where he is. What can he do? He can move left, he can move right, he can stop, right? That's about it. It's linear motion. And AB and BC both need to know how to do linear motion. BC, y'all, later on in the third 9 weeks, we're going to get into motion around a 2-dimensional plane, vector calculus, okay? So just imagine we got a little particle. You can name him something if you want, like Joseph, right? Because every unicorn should have a name. Particle Joseph, he moves on a horizontal line so that his position at any time. Now, when you read carefully, you might be given something like this that seems so innocuous at the time, but later on it may come back to be very important. So this is saying that t is greater than or equal to 0. This is probably your independent variable, and we don't want to dismiss negative time values out of hand because sometimes they can't help us predict back to something that happened before we arrived. But in this problem, t is 0 or bigger, okay? Know that. Its position then is given by this. So that's a pretty typical thing to do. If a particle is moving left and right, we'll call its position on that x-axis x of t. If it ends up moving on a vertical line, we typically call its position y of t, all right? So x is its horizontal placement on the number line at t, all right? And it's a quadratic. Now, do we have units? Yeah. X is measured in feet, right? So like, here's the number line, 1, 2. We're just pretending like that's 1 foot away, 2 feet away. Got it? And t is measured in seconds. So now we're on unit alert. Unit alert. Every final numeric answer must have the dependent variable units on it. You don't have to show the independent variable, but units on your final numeric answer. And every sentence that you possibly write will have to have both independent and dependent units on it. Okay, here we go. Look at all these questions. All right. Who knew that you could ask so many questions about a little particle? Find the displacement of the particle during the first 3 seconds. Explain its meaning. Okay. Do your math homework, right? Displacement is your net change in position. Net change in position. It's actually a vector. It's actually a vector. Okay. So if you imagine me, we don't have to imagine me. I'm standing right here. I'm standing in front of you. Okay. If I move 2 steps to your right, and then I move 1 step back to your left, I've traveled 3 steps, right? But what's my displacement? Positive 1, 1 step to the right. Very good. If I start here in front of you and I go 4 steps to y'all's left, and then I move 2 steps back to your right, I've traveled 6 steps. That's the distance I've traveled. But now my displacement is -2. Negative means to the left, okay? On the number line, positive is always to the right. That's where bigger numbers are found, positive. Negative is always to the left. So my displacement would be -2, right? If I took 2 steps to the right and 2 steps back to the left, my distance traveled would be 4, but now my displacement is 0, okay? So displacement is your net change in position. It's a vector during the first 3 seconds. So what we want to do now is identify the interval of time. This is not a calculus question because we have an interval. So that's going to be from t equals epsilon or t in epsilon 0 to 3. You wouldn't necessarily have to write that out, but it helps you identify it. And I'm going to put seconds on the outside. Or if you want to write it like this, 0 less than or equal to t less than or equal to 3. You're just identifying the interval. Okay, now define displacement. Here it is. Displacement, DISP. You want to get in the habit of labeling your expressions. Displacement, or you can call it big D, whatever. It's going to be your final position. Okay. So what would be the final position? It would be x of 3 minus your initial position, x of 0. Okay. So this would be final minus initial. If you do initial minus final, you're going to get what's called the opposite of displacement, and you're going to get it wrong. Okay. Final minus initial. All right. So now that we've got it set up, this would like earn a check, just FYI, because that's indicating your method. And now all we got to do is evaluate it. Okay. So let me pull this over here. I'm going to try and work straight down. X of 3. How do I find x of 3? Well, I plug it in right here, right? 3 squared is 9. This is going to be 9 plus 3 is 12. And then I get 12 minus 12. That's 0, right? Minus, when you plug in a 0, you get 3. So a little bit of calculating there. And that ends up being -3. Is that a final numeric answer? Yeah, so I now put units, which is feet, or FT for feet. Yeah. Now, again, on a free response, you could leave it as 0 minus 3 if you want. But at that where you would stop, you'd put FT at the back end, okay? -3 feet. Now, we have to write a sentence, okay? So during the first 3 seconds, we'll use the terminology. During the first 3 seconds, and there's the units, right? I have my units during the first 3 seconds. Or you could say from t equals 0 to 3 seconds, like we wrote up there, comma, the particle is displaced. And now anytime you write a sentence, you always interpret the sign, which is in this case a direction. A lot of times it's a rate, so it's increasing, decreasing, and then the scalar. So you break it down, the vector part from the direction and the scalar. So it's displaced 3 feet. There's a numeric answer, and with the units. And then what would the negative mean? Left. It's displaced 3 feet to the left. There you go. Now, if you want to add something in the end, you could say to the left of its starting position, but that's implied, right? During the first 3 seconds, the particle is displaced 3 feet to the left. Got it? Yeah. All right. Now, does that mean that it only traveled 3 feet during that time? Not necessarily. Very good. Not necessarily. All right. So that's not even calculus. Part B, find the average velocity during the first 3 seconds. Explain its meaning. Well, this is not calculus either. It's average, right? This is algebra 1. Now, this is important because this is going to end up being the difference quotient, which I'll just call dq. So average velocity equals, get in the habit of labeling your expressions. How do we find average velocity? Well, it's the average rate of change of position. So it's going to be your displacement over time. I think in your physics class, if you write that, a lot of people say it's displacement over time. You know, that's how they remember it. But really, it's displacement over elapsed time. For us, it's the difference quotient. It's x of 3 minus x of 0 all over 3 minus 0. And that's what you need to show. Your difference quotient. It has to be a quotient of 2 things in the top and 2 things in the bottom that are either added or subtracted. We all know 3 minus 0 is 3, right? Most of us. But we still want to write 3 minus 0. Okay. Now, why does that work? Let's look at the units. Stoichiometry, if you will, dimensional analysis. What are the units of the numerator? X, feet, right? What are the units of the denominator? Time, seconds. If you were to read that, feet divided by seconds is feet per second. Is that what we measure velocity in? Yes. Okay. So that is your displacement over time. So now we could just plug in, and I'm going to work left to right. Don't have a lot of room to work down. Hey, we did the numerator in the previous problem, didn't we? So we don't have to reinvent the wheel. We can import it, and then we put 3 in the bottom. You could stop there on a free response, but this, of course, is -1, and then feet/second. Okay. Now, when it says to explain the meaning, here's the thing with velocity. Velocity could always be explained 2 different ways. So you would actually be told how to explain it. So let's go ahead and do it both ways. The first thing we're going to do, though, is say during the first 3 seconds, comma, and then the first way to do it is in terms of the velocity. Okay, so you could say the particle averaged, and then we interpret as 1, +1 feet per second to the left. The particle averaged 1 foot per second moving left. All right. Does that mean it was moving left the whole time? No. So that would be answering it in terms of speed and direction. But the other way to do it would be in terms of what's happening to the position. It's the rate of change of position. So then you could say during the first 3 seconds, comma, the particle stick that on average adverbial clause in there anywhere. The particle on average moved left 1 foot each second. So in the first one, we're talking about speed, and so we answer in speed units. The second one, we're talking about its position, so we answer in position units. Okay, and it'll tell you. It'll say in terms of the particle's position, okay, or in terms of the particle's speed. So that's really only with velocity where we interpret it two ways. Okay, so we have an understanding of speed in its own right, but remember, it's still the rate of change of the previous quantity. All right. All right, so that still wasn't even calculus. Is there any calculus in this class at all? Well, let's see. Find the particle's initial velocity and its velocity at t equals 3. At t equals 3. At a single moment. Oh, that's not an average rate of change now. That's an instantaneous rate of change. What time is it? It's time to bust out the calculus. Oh, yeah. So I want to find v of 3. Well, before I can find v of 3, I need to find v of t. So let me go ahead and bring this, x of t from above, tunnel vision here, t squared minus 4t plus 3. Okay. How am I going to get the instantaneous equation for velocity? The derivative, right? Now, you don't have to put d dt out front. If you want, you can, but it's implied. When you put x prime of t, that's the very least that you need to show, because that indicates what you're doing, right? I'm going from x of t to x prime of t. But when it comes time to use it, man, it would be helpful to give it its own name outright, and it'll help us understand what we're doing. So what could we call that equation? V of t, right? So you can have both of those or just x prime of t. Do you think it would be okay just to call it v of t and not have x prime? No, because now you're not telling anybody how you're getting this new equation. It is appearing just out of nowhere. So you're not communicating, you're not indicating your method. So let's give it a new name. And now the power rule, right? So it's 2t minus 4. Boom. And now there's two different times. The initial velocity, that corresponds with t equals what? 0. So let's go ahead and do that. We'll say v of 0. Because I've defined what v is, I can now use it exclusively. If you didn't want to do that, you can call it x prime of 0. And now we plug in and we get -4. What would the units be? Feet per second. Okay. And then explain the meanings of each. So let's come over here now and do v of 3. V of 3, when you plug it into our derivative equation, is 6 minus 4, which is 2 feet per second. Okay, good. We should probably put BOTC here. BOTC. Now to explain it, again, I'm going to explain them each differently. I'm going to explain this one in terms of the speed and direction. And again, the instructions will tell you which one to use. And I'm going to explain this one in terms of the position. So they both start the same way, right? At, and then your independent variable. In this case, at t equals 0 seconds, comma, the particle is moving which direction? Left, yep, because that's the negative, and then at 4 feet per second. We have units on our input and our output. So that's what it would the instruction would say. Explain the meaning of your answer in terms of the particle's speed and direction. Okay, that's what it would be. It could also say, explain the meaning of your answer in terms of the particle's position, because that's what velocity is. It tells us how position is changing. So let's do that sentence over here. This would be at t equals 2 equals 3 seconds, comma, the particle the particle's position is whating. Yeah, it's a positive 2 now, right? So is increasing by 2. And then what do I write? Do I write feet/second? Good. I put at 2 feet and then each second or per second or every second. Okay, so in that case, we're talking about position and we answer it in position units. So that typically is only with velocity where you might be asked to explain it in 2 different contexts, okay? That's about all the time we have for today. But now that we kind of have an idea of what's going on, we should be able to finish this set of notes tomorrow after the math club meeting. I'll go a little bit faster. Y'all seem to be getting this, right? We will be missing some. I'm not going to teach during the math club meeting. I mean, obviously, but y'all will be back after the after advisory, right? Oh, you won't be here at all.